Humanity stands at the threshold of becoming an interstellar species. This vision of charting the unknown, the future of space exploration and interstellar travel, is the next great chapter in our story. Scientific breakthroughs are transforming science fiction into tangible reality right now. The stakes could not be higher, as the solutions to global challenges and the keys to new resources wait for us in the cosmos. By the end of this journey, you will understand the technologies and missions that are reshaping humanity's destiny. We will uncover what it truly takes to cross the void between stars and what we might find when we arrive. How do you picture humanity's place in the cosmic ocean a century from now? The dream of reaching for the stars is etched into our oldest stories. Long before launch pads and mission control, ancient civilizations mapped the constellations, seeing not just points of light but destinations for the human spirit. This curiosity slowly built the staircase we would one day climb. When Galileo first turned his telescope toward Jupiter, he did more than spot moons. He shattered the idea that Earth was the solitary center of all things. That single act of observation opened a door, and through it walked visionaries like Konstantin Tsiolkovsky, who calculated the mathematics that could lift us from our world. He saw that a rocket was the key, a vehicle that could carry humanity's aspirations on a column of fire. This theoretical groundwork found its explosive expression in the 20th century. The space race was more than a political competition. It was a global proving ground. The seemingly impossible became routine as satellites circled the globe and probes flew past distant planets. Then came the ultimate proof of concept, the Apollo moon landings. When a human footprint was pressed into the lunar dust, it was a message to the future, a declaration that we were no longer bound to our home planet. But the dream did not stop at the moon. Thinkers like Carl Sagan used the Voyager probes as cosmic messengers, while Arthur C. Clarke envisioned space elevators and journeys to Jupiter. They painted a picture of a future where the stars themselves were not just points of light but ports of call. This entire historical arc, from the first stargazer to the last moonwalker, has delivered us to this precise moment. We stand on the foundation they built, and now we are ready to examine the tools that will take us to the next level. The blueprints for interstellar travel are already being drawn. Chemical rockets got us to the moon, but they will not take us to the stars. The fuel required for such a journey under our current technology would be astronomical, a self-defeating mountain of propellant. We stand at the edge of a new era, one defined by propulsion systems that sound like they are pulled from science fiction, yet are the subjects of serious scientific inquiry. The fundamental limitation is known as the tyranny of the rocket equation. In simple terms, this means that to go faster, you need more fuel, but that extra fuel makes your spacecraft heavier, which then requires even more fuel to move. It is a vicious cycle that puts the stars frustratingly out of reach for conventional engines. To break this cycle, we must look beyond chemical combustion. One promising path leads to nuclear thermal rockets. These engines use a nuclear reactor to superheat a propellant like hydrogen, creating thrust that is far more efficient than any chemical reaction. A mission to Mars that currently takes many months could potentially be shortened to just a few weeks with this technology. But for true interstellar travel, we need to think even bigger. Imagine containing the power of a star within an engine. Fusion rockets aim to do just that, harnessing the same process that lights the sun to create immense and sustained thrust. The fuel for such a system, isotopes of hydrogen found in seawater, is virtually limitless here on Earth. Then there is the ultimate theoretical power source, antimatter. When matter and antimatter meet, they annihilate each other in a perfect conversion of mass to energy. An antimatter engine could potentially accelerate a spacecraft to a significant fraction of the speed of light. The challenge, of course, is producing and containing even a minuscule amount of this volatile substance, a task that currently requires facilities larger than a football field. On the more speculative frontier, concepts like the M-drive claim to generate thrust without any propellant at all, seemingly bending the known laws of physics. While intriguing, such ideas remain highly controversial within the scientific community, lacking the robust peer-reviewed evidence required for validation. The common thread weaving through all these concepts is the need to manipulate physics itself, to find a loophole in the cosmic rulebook that dictates how things move. But building an engine capable of such a journey is only one part of a much greater challenge. Once we have a vehicle that can cross the immense void, we must create a world within it, a self-sustaining ecosystem that can protect and nurture its human cargo for generations. Building a Starship engine is a monumental feat of physics, but the true test lies in keeping its human passengers alive, sane, and healthy across a journey that could span centuries. This vessel must become more than a machine. It must transform into a miniature world, a self-contained biosphere hurtling through the absolute emptiness between stars. Our current experience aboard the International Space Station provides a starting point, but only that. Its systems are remarkably efficient, recycling around 90% of the water astronauts use, yet the station remains tethered to Earth, dependent on regular cargo deliveries for air, food, and spare parts. For an interstellar mission, that tether is severed forever. The ship must achieve a near-perfect closed loop, recycling 100% of its water and air, and generating every scrap of food its inhabitants will ever eat. This is the grand challenge of bioregenerative life support. Imagine vast chambers within the ship, not filled with machinery, but with thriving gardens under artificial suns. Projects like NAS, a biohome, and the European Space Agency's MILISSA are already pioneering this future on Earth. They are creating sealed environments where specific plants and microorganisms work in concert, breaking down human waste into nutrients, purifying water, and producing fresh food and breathable oxygen in a continuous, life-giving cycle. The ship itself would breathe and grow along with its crew, yet the human element is as fragile as any technological system. Confinement in a metal can for decades, with the same handful of faces and the unchanging view of star-streaked blackness, presents a profound psychological trial. Habitat design will be critical, moving far beyond mere functionality. We will need spacious communal areas to foster social bonds, private quarters for solitude, and immense innovation to combat the mind-numbing monotony. Virtual reality could offer portals to forests and beaches, while artificial windows might display not just the void outside, but simulated landscapes to soothe the soul. Every element of daily life must be engineered to support mental resilience, because a mission cannot fail due to a broken spirit, and everything from the air scrubbers to the food processors must be built to a standard of reliability we can barely conceive of today. There will be no rescue, no repair mission, no spare parts delivery when you are millions of miles from home. A single critical failure would mean the end. Mastering the art of sustainable living within a starship is the necessary rehearsal for an even grander stage. It prepares us to create permanent homes not just on the journey, but at the destination where we might construct entire cities under alien skies. The very structure of our civilization in space will be built from the cosmos itself. Instead of hauling every beam and bolt from the bottom of Earth's deep gravity well, We will learn to live off the land, turning asteroids and barren moons into the shipyards of a new age. The International Space Station is our first humble outpost, a testament to what we can achieve when we maintain a continuous presence in orbit. But the structures that follow will dwarf it, transforming from experimental modules into sprawling industrial hubs and permanent settlements. In the pristine microgravity of orbit, factories could manufacture wonders. They could grow perfect crystals for next-generation computer chips, formulate life-saving drugs with a purity unattainable on Earth, and create metal alloys of unprecedented strength. This is not merely about making things in space for use in space. It is about revolutionizing industry for everyone back on our home planet. The journey to this future is already being mapped. NASA Artemis program is not just about returning boot prints to the lunar surface. It is about laying the groundwork for a sustained human presence. The moon will become a cosmic workshop, a place where we test the technologies and techniques for extracting water ice from the soil and converting it into breathable air and rocket fuel. This is the crucial first step in breaking our dependence on Earth. Private visionaries are pushing the concept even further. Companies like SpaceX are designing massive, next-generation starships, vessels so large they must be constructed in the vacuum of space itself, destined to ferry hundreds of passengers between worlds without ever landing on a planet. This monumental task demands a new kind of engineering. We will need autonomous robots that can assemble giant structures under human supervision, and sophisticated three-dimensional printers that can fabricate components using dust from the lunar surface or metals mined from passing asteroids. This shift from exploration to construction marks a fundamental change in our relationship with the universe. We are no longer just visitors taking pictures. We are becoming tenants, building a home among the stars. And with these new shipyards and way stations in place, our gaze can finally turn with purpose toward the specific destinations that beckon from the darkness. Orbiting the moon, the Lunar Gateway will be humanity's first outpost in deep space, a celestial port of call for a new era of exploration. This small, modular station is far more than a repeat of the International Space Station. Its location is a masterstroke of orbital mechanics, positioned in a path that makes it surprisingly efficient to reach from Earth while granting it a panoramic view of the entire lunar surface. This strategic perch transforms the moon from a distant destination into a convenient backyard. The gateway will be a bustling hub, a place where astronauts can live and work for months, descending to the lunar soil in landers for surface expeditions and then returning to their orbital home. But its purpose extends far beyond the moon itself. It is a dedicated testbed for the technologies we will need to survive the much longer journey to Mars. One of its most critical roles will be to study a danger we cannot see or feel until it is too late: deep space radiation. Shielding on the gateway and experiments conducted there will teach us how to protect human biology from the constant, invisible barrage of cosmic rays, a puzzle that must be solved before we can send astronauts safely into the true depths of the solar system. The station itself will be a demonstration of next-generation engineering, likely powered by advanced solar electric propulsion. This technology uses solar power to create incredibly efficient thrust, a method perfect for slowly but steadily moving large structures through space while consuming a fraction of the fuel of conventional rockets. The gateway represents a fundamental shift in our strategy. We are no longer planning flags and footprints missions. We are building infrastructure. This is the first permanent foothold beyond the fragile cradle of low Earth orbit, a declaration that we are here to stay. And from this new vantage point, a rusty red dot in the night sky begins to look a little closer, a little more reachable. That rusty red dot is more than a planet, it is a promise. Mars awaits not as a destination for brief visits, but as the future home for our first interplanetary civilization. The first human footprints pressed into its ruddy soil will not be those of tourists who leave, but of settlers who arrive to stay. This vision transforms Mars from a scientific curiosity into a profound human endeavor. Its appeal is rooted in practical realities. A day on Mars is just over 24 hours long, a familiar rhythm for earthly biology. Crucially, frozen water lies trapped beneath its surface and at its poles, the fundamental resource for life and fuel. Yet for all its promise, Mars is a harsh and unforgiving landlord. The journey itself exposes travelers to a relentless bath of cosmic radiation, a danger that continues on the surface under an atmosphere too thin to provide a reliable shield. The very soil is laced with perchlorates, toxic chemicals that make it poisonous to earthly life. Before a true colony can flourish, it must solve the ultimate puzzle of self-sufficiency, creating everything from food and air to spare parts and medicine, long before regular resupply from Earth is even possible. This grand challenge has inspired two distinct pathways. One, championed by Elon Musk and SpaceX, is driven by an ambitious vision of a city of 1 million people, a goal that fuels the rapid, iterative development of the massive Starship vehicle. The other, embodied by NASA, a methodical approach, prioritizes scientific discovery and risk reduction, establishing a foothold through rigorous research before committing to permanent settlement. Both paths converge on the same critical technology, using what is already there. This is the art of in-situ resource utilization. Rovers will not just study the Martian landscape, they will become miners and chemists. They will drill into ice deposits, melt the water, and split it into breathable oxygen and hydrogen for rocket propellant. They will pull carbon dioxide from the thin air, processing it to create methane fuel and even the basic building blocks for plastics. The colony will literally breathe and drink the Martian environment, learning to live off the land in a way that has never been attempted. Yet, the greatest obstacles may not be technological, but human. How does a small, isolated group, completely cut off from the cultural and social fabric of Earth, build a stable society? The psychological pressure of confinement, the monotony of an unchanging landscape, and the knowledge that rescue is impossible will test human resilience in ways we can only simulate. This new civilization will need to develop its own laws, its own customs, and its own shared identity to survive. Every lesson learned on Mars, from sealing a habitat against the thin air to managing the interpersonal dynamics of a closed community, is a direct rehearsal for the ultimate voyage. Mastering the art of living on a dead world is the essential training ground for the day we cast off for a living one, orbiting a star light years away. The resources of an entire solar system are waiting to be unlocked, and the key lies in the countless drifting mountains of rock and ice known as asteroids. These celestial bodies are far more than ancient relics. They are the untapped treasure chests that could power our entire future in space. Within them lie staggering concentrations of platinum, gold, cobalt, and other rare earth metals, materials that are becoming increasingly difficult and environmentally costly to mine on our home planet. But the true game changer is something far more fundamental: water. Locked within the icy grasp of certain asteroids is the lifeblood of exploration itself. A single water-rich asteroid could hold enough frozen water to fill a vast lake, and that water is not just for drinking. Through a process called electrolysis, it can be split into its basic components, hydrogen and oxygen, the very ingredients needed for the most common types of rocket fuel. This transforms a barren rock into a cosmic gas station, a pit stop for refueling that completely changes the economics of travel. Visionary companies like Planetary Resources and Deep Space Industries were among the first to seriously chart this new frontier, proposing fleets of robotic prospectors to survey and eventually extract these incredible resources. The initial targets will be near-Earth asteroids, those that drift on orbits bringing them relatively close to our planet, making the round trip a matter of months instead of years. The first phase of this industry will be entirely robotic, with autonomous spacecraft identifying, landing on, and processing raw materials without a single human hand guiding them. The technical hurdles are immense, from developing drills that can operate in microgravity to creating refineries that function in the vacuum of space. Yet the payoff is a fundamental shift in how we operate beyond Earth. Mastering the art of asteroid mining means we finally break the chains of Earth's gravity well. Instead of expending enormous fuel and cost to launch every single gram of water, metal, and fuel from our planet's surface, we can learn to live off the cosmic land. This capability, known as In-Situ resource utilization, is the ultimate enabler. It could slash the cost of constructing space stations and fueling Mars missions by orders of magnitude. The metals mined from a single asteroid could be used to build vast solar power satellites in orbit, beaming clean energy back to Earth, or to construct the skeletal frames of the very starships that will one day carry us to other stars. This is not just about wealth, it is about building a ladder. The economic engine of asteroid mining provides the fuel, the funds, and the foundational materials to lift our ambitions higher and higher, until one day we look back and see that the solar system has become our backyard. And as we learn to navigate and harvest these small worlds, our attention is inevitably drawn to the profound mysteries that lie on the worlds much larger than our own, the gas giants and their icy, ocean-bearing moons. Far beyond the orbit of Neptune, the solar system does not simply end. It gives way to a vast, dark frontier, a sprawling disk of icy worlds known as the Kuiper Belt. This is not empty space, it is a deep freeze preserving the raw ingredients of our planetary system. Out here, the sun is just a painfully bright star in an otherwise perpetual night, and temperatures hover near absolute zero. This region stretches from about 30 times the Earth-Sun distance to over 50 times that vast gap, a domain containing dwarf planets like Pluto and Eris, alongside millions of smaller, primitive objects. These are not merely frozen rocks, they are cosmic time capsules. Each one is a relic from the solar system's dawn over 4.5 billion years ago, composed of the original dust and ice that never coalesced into a major planet. By studying them, we are effectively reading the opening chapter of our own cosmic story, a chapter that has remained unedited since the beginning. Our first true glimpse into this frontier came from the intrepid New Horizons spacecraft. Its flyby of Pluto shattered our expectations of a dead, cratered world. Instead, we saw towering mountains of water ice, vast glaciers of frozen nitrogen, and hints of a subsurface ocean. This was a world alive with geological activity, a shocking discovery for a place so far from the sun's warmth. The mission's subsequent visit to the Kuiper Belt object Arakath was even more revealing. This bizarre, flattened snowman shape, formed from two gently connected spheres, is a preserved planetary building block. It shows us how the first seeds of planets gently merged in the early solar system, a process that was far more calm and orderly than the violent collisions we once imagined. Arakath is a fossil, a direct look at the construction blocks from which worlds like Earth were ultimately assembled. The next logical step is to push even deeper. Beyond the main Kuiper Belt lies the scattered disk, a region of unstable orbits where gravitational interactions with Neptune have flung objects into even more distant and elongated paths. And further still, we theorize the existence of the Oort cloud, a hypothetical spherical shell of icy bodies surrounding our entire solar system. This would be the true boundary of the Sun's gravitational influence, a reservoir of trillions of comets stretching nearly halfway to the next star. A future probe sent into this profound darkness would be our first emissary to the very threshold of interstellar space. The data it returns would be priceless, telling us not only about our own solar system's outer limits, but also providing a crucial preview of the kind of icy planetesimals we will likely encounter orbiting other stars. Understanding this final frontier is the essential groundwork for the journey to come. As we map the dim, frozen outskirts of our own solar system, we are essentially preparing for the day when we will navigate the similar but infinitely vaster spaces between the stars. The void between stars is not truly empty. It is a vast dynamic ocean through which our entire solar system sails, a realm of subtle currents and hidden dangers known as the interstellar medium. This is the environment our first starships must navigate, a sparse soup of gas, dust, and energy. On Earth, we measure air in quintillions of molecules per cubic centimeter. Out there, in the deep dark, you might find just a single, lonely atom in the same amount of space. Yet this near-perfect vacuum is far from tranquil. It is threaded with powerful magnetic fields and peppered with microscopic dust grains traveling at speeds faster than a rifle bullet. The Voyager probes, our first robotic envoys to cross this threshold, sent back startling data. As they passed beyond the Sun's protective magnetic bubble, they registered a dramatic surge in cosmic radiation and a fundamental shift in the magnetic field surrounding them. They confirmed that we are moving through a galactic ecosystem. For a vessel on a centuries-long journey, this environment presents a constant, grinding threat. Cosmic rays, which are high-energy atomic fragments, would steadily penetrate the ship's hull, posing a serious risk to both human health and sensitive electronics. Shielding becomes a primary design challenge, requiring innovative materials or even magnetic fields generated around the ship itself for protection. Then there are the micrometeoroids, those tiny, high-velocity specks of dust. A single impact, while minuscule, could, over time, erode the ship's exterior like a constant, invisible sandblaster. A slightly larger grain could puncture a critical system, ending the mission in an instant. Yet within this hazard also lies a tantalizing possibility. The interstellar medium is mostly hydrogen, scattered everywhere. This inspired the concept of the Bussard Ramjet, a theoretical engine that would use a gigantic magnetic funnel to sweep up this hydrogen as the ship moves. This collected hydrogen would then be used as fuel for a fusion reactor, creating a self-sustaining engine that needs to carry very little of its own propellant. The ship would essentially breathe the thin air of space to power its journey. The engineering, however, is monumentally difficult, creating a magnetic scoop large enough to collect a meaningful amount of hydrogen, and doing so without creating drag that would slow the ship more than the engine accelerates it, remains a puzzle we have not yet solved. Beyond these immediate engineering concerns, the interstellar medium is a scientific treasure. Its composition holds the frozen history of ancient supernova and the faint, complex chemistry that occurs on the surfaces of dust grains. These grains are thought to be the factories where simple molecules can form, including some of the basic organic compounds that are the precursors to life. By analyzing this cosmic material, we are reading the recipe for how planetary systems, and perhaps life itself, might be distributed across the galaxy. To sail the cosmic ocean, we must first understand its waters, its weather, and its hidden resources. Every challenge it presents forces us to become better shipwrights, and every secret it reveals brings us closer to understanding our own origins. And as we learn to navigate this great dark sea, we can finally turn our attention to the specific shores that await us, the exoplanets orbiting distant suns. That blueprint for an interstellar vessel already exists, meticulously drafted not in this century, but in the 1970s. Project Daedalus was the brainchild of the British Interplanetary Society, a team of engineers and physicists who decided to treat interstellar travel not as a dream, but as a straightforward engineering problem. Their goal was to design an unmanned probe that could reach another star within a single human lifetime, and they committed to using only physics that was already understood. The solution they arrived at was as audacious as it was logical, a two-stage behemoth powered by nuclear fusion. The engine would fire microscopic pellets of deuterium and helium-3 into a reaction chamber, where powerful electron beams would compress and ignite them, creating a continuous series of miniature star-like explosions. This controlled fury would propel the 50,000-ton spacecraft to an almost unimaginable velocity, 12% of the speed of light. At that pace, the journey to Barnard's star, nearly 6 light-years away, would take just 50 years. The probe would not slow down. It would be a high-speed flyby, a breathtakingly brief encounter. Its automated laboratories would have only hours or days to frantically study the alien star system, snapping pictures, analyzing atmospheres, and collecting data, transmitting its priceless findings back to a waiting Earth that would have aged decades since its launch. The sheer scale of Daedalus revealed the immense hurdles. Where would you find the enormous fuel supply, particularly the rare isotope helium-3? The project's answer was as staggering as the ship itself. It would have to be mined from the atmosphere of Jupiter, a feat that remains far beyond us. And the entire vessel would need to operate flawlessly, completely autonomously for half a century. There would be no repairs, no course corrections from mission control. The probe's computers would need the intelligence and resilience to handle any problem alone. While we lacked the technology to build Daedalus then, and still do today, its true legacy was a methodology. It proved that the void between stars could be crossed without invoking magic or unknown physics. It was a matter of scale, engineering, and will. This foundational work directly inspired a new generation of concepts that ask an even more profound question. If we could build such a ship, who would be brave enough to crew it? The audacity of Project Daedalus is humbled by a concept that turns the very idea of a starship on its head. Instead of a single, monumental vessel, picture a fleet of thousands, each individual craft smaller than a postage stamp. This is the radical vision of Breakthrough Starshot, an initiative aiming to sail nanocraft to Alpha Centauri, not on rocket fuel, but on beams of light. The core technology is a light sail, an incredibly thin and reflective membrane attached to a gram-scale chip. This chip is the entire spacecraft, housing miniaturized cameras, photon thrusters, a power supply, and communication lasers. The journey begins not in space, but on the ground, with a square-kilometer array of immensely powerful lasers, all focusing their energy onto the light sails as they deploy. The push from this concentrated light would be gentle at first, but continuous, accelerating the tiny craft to a staggering 20% of the speed of light within minutes. At that velocity, the 4.37 light-year trip to our nearest stellar neighbor would take just over 20 years, with another 4+ years for the data to travel back to us. Within a single human generation, we could receive the first close-up images of an alien world. The challenges, however, are as immense as the ambition. Constructing the laser array itself is a monumental engineering feat, requiring a level of power and precision that pushes the boundaries of current technology. Then there is the journey itself, the interstellar medium, which is mostly a harmless vacuum for a larger ship, becomes a deadly hailstorm for a stamp-sized craft. A collision with a single microscopic dust grain, no larger than a speck of pollen, would be catastrophic at these speeds, vaporizing the nanocraft instantly. Shielding is almost impossible due to the minimal mass, so the mission strategy might rely on sheer numbers, sending out thousands of sails with the hope that a statistically significant number survive the passage. Finally, even if a craft survives, how does it phone home? The tiny laser on its chip must be powerful and precise enough to send its precious data across the mind-boggling distance of over 4 light-years, a whisper that must be heard across a cosmic ocean. Success would be a paradigm shift, proving that our first step into the interstellar realm might not be a single grand ship, but a swarm of tiny, resilient messengers. It demonstrates that by thinking small, we can overcome the colossal energy barriers of interstellar travel. Yet, a fleeting flyby, no matter how revolutionary, only deepens the mystery of what lies in that alien system. The ultimate dream remains a mission that does not just fly past, but one that stays. A generation ship is a civilization in miniature, a world of its own sailing on a voyage that will outlast its original crew. This is not a mission for a single lifetime, but a covenant made with the future. Entire communities would live, work, and raise families within the metal walls of this ark, with generations being born, growing old, and passing away, all while the ship travels through the profound emptiness between stars. For the grandchildren of the original crew, Earth would be a story, a flickering image in an archive, while the ship itself is the only tangible reality they will ever know. This vessel must achieve a perfect closed-loop balance. Its atmosphere and water must be recycled with near 100% efficiency. Its food production must be utterly reliable, and its waste must be seamlessly reprocessed back into the system. It is an ecosystem in a bottle, one that cannot afford to fail. The social and psychological fabric of this isolated society would be tested in ways we can barely comprehend. How do you maintain the knowledge of the mission's original purpose across hundreds of years? How do you prevent a society from collapsing into apathy or rebellion when its ultimate goal is dozens of generations away? The culture on board would inevitably evolve, creating its own traditions, its own language, and its own unique identity, completely detached from the ever-changing cultures of an Earth they left behind. Current concepts for such arcs are staggering in their ambition. Some propose hollowing out a large asteroid, using its bulk as a natural shield against cosmic radiation. Others envision enormous rotating cylinders, miles in length, using centrifugal force to simulate gravity on their inner surfaces. These O'Neill cylinders, as they are often called, could contain rolling hills, rivers, and towns under vast, artificial skies, all contained within a spinning shell. Each design offers different trade-offs between protection, resource availability, and the sheer psychological benefit of living in a spacious, seemingly open environment. While the engineering hurdles are colossal, they may be simpler than the profound ethical questions this endeavor raises. Is it morally justifiable to bring children into a life where their entire existence is confined to a ship, their destiny preordained by an ancestor's choice? Do those unborn generations have a right to a world they did not choose? These are not questions for engineers alone, but for all of us, as a species contemplating its first steps into the galactic community. The generation ship is a testament to human patience and resilience, a way to conquer distance with time. Yet other ideas seek a more direct path, challenging the very nature of space and time to make the journey not a multi-generational saga, but a single lifetime. The universe provides its own loopholes in the cosmic speed limit, written in the language of general relativity. While conventional propulsion battles the immense distances between stars, another approach asks a more profound question. What if we did not have to cross the distance at all? What if we could bring the destination to us or create a tunnel directly through the fabric of reality? This is not pure fantasy, but a frontier of theoretical physics that hinges on manipulating spacetime itself. In 1994, physicist Miguel Alcubierre proposed a mathematical model for a warp drive. His solution to Einstein's field equations described a method where a spacecraft could ride a wave of distorted spacetime. The craft itself would sit inside a stable bubble, a pocket of normal space. In front of the bubble, spacetime would be massively compressed, pulling the destination closer. Behind it, spacetime would expand, pushing the point of origin away. The ship would not move through space faster than light. It would be space itself that was moving, carrying the vessel along like a surfer on a wave. This elegant idea, however, comes with a monumental catch. Creating and sustaining this warp bubble requires a form of exotic matter that possesses negative energy density, a substance that would gravitationally repel rather than attract. While certain quantum effects suggest tiny amounts of this negative energy might be possible, whether it exists in the vast, stable quantities needed to power a starship is a complete unknown. Wormholes present another tantalizing shortcut. Often visualized as tunnels connecting two distant points in spacetime, these theoretical structures could turn a journey of light years into a trip of mere miles. The entrance or mouth of a wormhole might be near Earth, while the exit could open up in the Alpha Centauri system. You would simply step through, but just like the warp drive, the stability of a traversable wormhole is the problem. According to our current models, the tunnel would likely collapse instantly under its own gravity, crushing anything inside. The only way to prop it open, to keep the throat from snapping shut, would be to thread it with the same exotic, negative energy matter required for the Alcubierre drive. The pursuit of these ideas is not confined to blackboards. Laboratories like NASA Eagleworks are conducting tabletop experiments to see if microscopic effects of warp fields or other spacetime manipulations can be detected. They are testing these theories at a scale smaller than a single atom, searching for any faint signature that the math might translate into physical reality. The work is painstaking and the results are preliminary, but its very existence signals a serious scientific interest. These concepts push our understanding of physics to its absolute limits, forcing us to reconcile the cosmic rules of relativity with the bizarre quantum rules of the very small. Even if a functioning warp drive remains a dream for millennia, the investigation itself deepens our grasp of the universe's fundamental blueprint. It keeps alive the most audacious hope that one day we might not be limited by the speed of light, but empowered by the malleability of the cosmos. Yet all these shortcuts, whether bending space or boring through it, lead us to the same essential need. Before we can step through any doorway to the stars, we must first know what lies on the other side. Our galactic neighborhood is far more crowded than we ever dared to dream. The once abstract question of where we might go has been answered with a staggering abundance of choice, as missions like Kepler and TESS have revealed a cosmos teeming with worlds. These telescopes did not find planets by seeing them directly in most cases. Instead, they watched for the subtle, repeating dimming of a star's light, a telltale shadow cast by an orbiting world crossing its face. This cosmic census has yielded a revolutionary statistic. For every star you see in the night sky, there is likely at least one planet. Statistically, that means our Milky Way galaxy alone could be home to billions of Earth-sized planets orbiting within their star's habitable zone, that Goldilocks region where temperatures might allow liquid water to pool on the surface. The dream of interstellar travel is no longer a journey into the complete unknown. We now have a map, and it is filled with potential ports of call. One of the most compelling destinations lies just 39 light-years away, orbiting a small, cool red dwarf star called TRAPPIST-1. This single system is a miniature solar system of its own, boasting 7 rocky planets, all roughly the size of Earth. 3 of these worlds orbit snugly within the star's habitable zone. Imagine the view from any one of them, where the sky would be filled with the looming, magnificent orbs of your neighboring planets, each a distinct world with its own geography and mysteries. This compact arrangement makes TRAPPIST-1 a prime target, a system where one mission could potentially study multiple potentially habitable environments. The next step is to move from detecting these worlds to truly understanding them. The James Webb Space Telescope is our key to this new level of discovery. Its powerful infrared eyes can dissect the starlight filtering through a distant planet's atmosphere. By analyzing this light, scientists can determine the chemical composition of that alien air. They will be searching for biosignatures, specific combinations of gases that are difficult to explain without the presence of life. The persistent, abundant oxygen in Earth's atmosphere, for example, is constantly replenished by living organisms. Finding a similar signature around another world would be a profound, if not definitive, indicator that we are not alone. This data is not just about the search for extraterrestrial life, it is the ultimate mission planning tool. Before humanity commits to a centuries-long voyage to another star, we will want to know which planets have clear, oxygen-rich atmospheres, which are shrouded in the acidic clouds of a runaway greenhouse effect, and which are barren rocks. The information sent back by Webb and its successors will help us prioritize, allowing us to aim our first interstellar probes, and eventually our generation ships, at the most promising worlds in the cosmic ocean. The continuing flood of exoplanet discoveries constantly reshapes our understanding of what is possible, revealing water worlds, lava planets, and super-Earths that have no counterpart in our own solar system. Each new world expands the horizons of where life might take root and where humanity might one day find a second home. But identifying a potentially habitable world from a distance is one thing. The true challenge begins when we finally arrive in orbit and turn our sensors toward the surface. The profound silence of the cosmos is perhaps its most tantalizing mystery. Our interstellar ambitions force us to confront a fundamental question: are we destined to be cosmic loners, or are we on the verge of finding company? The search for extraterrestrial intelligence, or SETI, represents humanity's collective ear perpetually cupped toward the stars, listening for a whisper of artificial origin. This is not a passive endeavor. Modern SETI initiatives employ incredibly sophisticated algorithms to sift through the constant cosmic static picked up by radio telescopes like the Allen Telescope Array. These programs are not just listening for any signal, they are hunting for a pattern that nature alone could not possibly produce, a structured message encoded in the radio waves. Finding even the simplest microbial life on Mars or within the subsurface ocean of Europa would instantly revolutionize biology, proving that the genesis of life is not a singular miracle on Earth, but a common cosmic process. But the discovery of a technological intelligence, a civilization capable of sending or receiving signals, would represent a watershed moment for all of human history, fundamentally reshaping our philosophy, our science, and our understanding of our own place in the universe. What would such a discovery mean for our future among the stars? Existing protocols for first contact, drafted by international committees, outline cautious steps for verification and communication. Yet, how can any document truly prepare us for an event of such magnitude? ethicists and scientists debate whether our first impulse should be to reply with open arms or to observe in cautious silence. The implications for interstellar travel are staggering. Would we find eager collaborators, beings with whom we could share knowledge and chart the galaxy together? Or would we encounter competitors for resources, leading to a cosmic expansion fraught with new kinds of peril? There is a third, more somber possibility. We might not find thriving civilizations at all, but only their silent archaeological ruins. The apparent quiet of the universe has led some to propose the chilling Great Filter hypothesis. This idea suggests that some nearly insurmountable barrier, perhaps a self-destructive technological phase or a natural cosmic catastrophe, prevents the vast majority of civilizations from ever achieving interstellar travel. The silence, then, could be a cemetery quiet. Our drive to reach other stars is in itself a test of whether we can overcome whatever filter may lie in wait. Whether we ultimately find the galaxy teeming with life or hauntingly empty, the very act of searching reframes our existence. It forces us to look beyond our planetary disputes and see humanity as a single entity, poised on the brink of a cosmic community or facing a profound solitude. This search for cosmic companionship is the deepest context for our journey, a quest that will define us long before we ever arrive at a distant world. Our technological reach is expanding at a breathtaking pace, but our moral compass must be calibrated for the profound consequences. The silent, pristine plains of Mars or the hidden oceans of Europa may hold fragile, nascent life, and our arrival poses an existential threat to it. This is the heart of planetary protection, a principle that currently demands we bake our robotic probes in ovens to incinerate any microbial stowaways. It is a practice of cosmic hygiene, an acknowledgement that we could inadvertently smother alien biology before we even know it exists. But how does this careful stewardship apply when the visitors are not sterile machines, but breathing, sweating, microbe-shedding human colonists? If we find a thin scum of Martian bacteria clinging to a subsurface aquifer, does that entire world become a protected wilderness, off limits for settlement? Or do we become cosmic gardeners, carefully sectioning off preserves while we terraform the rest? The answers are not simple. Some argue that humanity's survival is the ultimate ethical good, justifying expansion wherever possible. Others contend that destroying even the simplest alien life form would be an act of unforgivable cosmic vandalism. This debate extends beyond biology to the very act of spreading. The concept of a generation ship is a breathtaking engineering solution, but it raises a stark question of consent. The children born inside that metal world never chose the mission. Their entire universe is a predetermined voyage to a destination they will never see, their lives dedicated to a purpose set in motion centuries before their birth. Is it ethical to create a lineage of humanity that knows no other home, that serves a goal they did not choose? We must build a society resilient enough to avoid fracturing under this unique pressure, a culture that can maintain meaning and hope across generations. This touches on the deepest philosophical divide regarding our place in the cosmos. Is life a rare flame that we have a sacred duty to spread, carrying its embers to every habitable world we find? Or is unchecked expansion a familiar pattern of colonial impulse, one we should be wise enough to avoid repeating on a galactic scale? Our rockets and life support systems are being designed today, but the ethical framework that will guide their use is still being written. The choices we make now, before we take those irreversible steps, will define our legacy not just as a species that could travel to the stars, but as one that was wise enough to do so rightly. The sheer scale of an interstellar vessel demands a budget that dwarfs the entire history of space spending. we are no longer contemplating a single mission, but a project that would span generations and require a fundamental shift in how we fund our cosmic ambitions. The current global space economy, valued at around $400 billion annually, is a thriving marketplace of satellites and rockets, yet that entire sum is a mere fraction of what would be needed to construct and launch a ship capable of reaching another star. The price tag for such an endeavor could easily reach into the trillions, a figure that places it on par with terrestrial undertakings like global climate change mitigation or a world war. No single nation, not even the wealthiest, could or would bear this cost alone. This forces us to invent new economic models, frameworks for cooperation that transcend borders and short-term political cycles. One path forward is the formation of an international consortium, a global partnership where nations pool their resources, talent, and political will for a shared generational goal. This would be a modern cathedral project, built not by a single kingdom but by all of humanity. Alternatively, we might see the rise of philanthropic giants, individuals whose wealth and vision could catalyze the first critical steps. Just as historical patrons funded great expeditions and art, a modern Medici could see their legacy not in a painting but in a starship. There is also the untapped power of the crowd. A mission that truly captures the global imagination could be funded in part by millions of small contributions, a symbolic investment from ordinary people in an extraordinary future. But the most sustainable path may lie in the cosmos itself. The nascent industry of asteroid mining promises to create wealth on an unprecedented scale, generating capital from the resources of space rather than draining the treasuries of Earth. The profits from harvesting precious metals and water from asteroids could directly fund the construction of interstellar arcs, creating a self-perpetuating economic engine for expansion. The ultimate economic argument, however, is one of survival. A self-sustaining interstellar civilization represents the ultimate insurance policy for humanity, a safeguard against any single catastrophe that could befall our home planet. This shifts the financial calculus from one of pure exploration to one of existential necessity. Funding such a long-term venture requires a radical rethinking of value itself. How do we justify an investment whose dividends may not be realized for 500 years? How do we build an economic system that values the future with the same weight as the present? The challenge is not merely one of engineering, but of collective will. Throughout history, humanity has consistently funded what it truly values, from the Great Pyramids to the International Space Station. The question before us now is whether we value a future among the stars enough to pay the price. This financial architecture will determine the pace of our journey, but the destination itself remains a world of profound unknowns, a place where our very definitions of life and intelligence will be tested. The immense scope of an interstellar voyage demands a new model of human enterprise, one that transcends any single nation or corporation. This journey will not be a solitary flag planted in alien soil, but a collective endeavor requiring the unified effort of our entire species. We already possess a powerful blueprint for this kind of collaboration. The International Space Station stands as a testament to what is possible when old rivalries are set aside for a common goal. For over 2 decades, the United States, Russia, Europe, Japan, and Canada have maintained a continuous human presence in orbit, a fragile outpost of cooperation that has weathered political storms on the ground. This partnership proves that shared objectives in space can create unbreakable bonds. To reach for the stars, this circle of cooperation must widen dramatically. It must embrace the burgeoning space capabilities of China and India, the ambitious visions of the United Arab Emirates, and the relentless, disruptive innovation driven by private companies like SpaceX and Blue Origin. Each brings unique strengths, from manufacturing scale to cutting-edge propulsion research, forming a global ecosystem of talent and resources. Yet, such a vast alliance cannot operate in a legal vacuum. The existing Outer Space Treaty, which declares space the province of all humankind, provides a foundational principle, but it will need to be expanded with new frameworks to address the novel challenges of interstellar travel. Who has the right to use resources on an exoplanet? How do we prevent conflict light years from Earth? Establishing these rules of the road before we launch is not just bureaucratic, it is essential for maintaining peace on a journey that will last for generations. Some philosophers and scientists suggest that this very process, the act of uniting for a goal so grand, could be the catalyst that finally helps humanity overcome its ancient terrestrial conflicts. The shared challenge of building a starship offers a unifying purpose that makes national borders seem as arbitrary as they truly are from orbit. The organizational structures we invent to manage this cooperation, the international agencies and treaties, may ultimately be as vital to our success as the engines that propel us. They represent the social technology required for our survival among the stars, and it is within these carefully built structures that the most human of all challenges will unfold as we confront the profound psychological weight of leaving our home world behind forever. The fragile human mind may be the final frontier for interstellar travel. While we can engineer shields against radiation and perfect closed-loop life support, we cannot as easily fortify the psyche against the relentless grind of deep space. The psychological profile required for such a mission is unlike any other. It is not about the right stuff of heroic pioneers, but the resilient stuff of stable, adaptable community builders. We already have glimpses of these challenges from extreme environments on Earth. Scientists overwintering in Antarctica face months of unbroken darkness and confinement, where small irritations can fester into major conflicts. Submarine crews operate in a steel tube for months, mastering the art of coexistence in a space where there is no escape from one another. Astronauts on the International Space Station train for years to handle the intense pressure, yet even they speak of the profound longing that comes from watching the world turn below, a beautiful but constant reminder of everything they are missing. An interstellar journey magnifies these stressors to an almost unimaginable degree. The monotony would be absolute, a daily routine with no changing seasons, no new scenery beyond the fixed starfield, and the same small group of faces for decades. Interpersonal conflicts would not be temporary crises to be managed, but permanent conditions that must be navigated with extraordinary emotional intelligence. The most heart-wrenching challenge, however, is the separation. This is not a 6-month tour on the space station with video calls home. As the ship moves farther from Earth, the time lag for communications stretches from minutes to years. A message from home would take decades to arrive, and a reply would take decades to return. The crew would eventually be living on historical news, cut off from the living, breathing culture they left behind. They would be raising children who know Earth only as a story. To combat this, we must design well-being into the very fabric of the ship. Virtual reality would not be a luxury, but a vital utility. It could offer portals to a forest walk, a bustling city street, or a quiet beach, providing essential sensory variety and a psychological escape from the metal walls. Habitat design will be critical, moving beyond sterile efficiency to incorporate warm, natural aesthetics, dynamic lighting that mimics a day-night cycle, and spacious communal areas that foster a sense of community rather than claustrophobia. Perhaps the most profound psychological test is what some theorists call Earth out of view depression. There is a powerful psychological anchor in seeing that bright blue marble hanging in the void. The day it shrinks to become just another star and then vanishes entirely will be a milestone unlike any other. It is the moment the tether is truly cut, a visceral confirmation of isolation that could trigger a deep existential crisis. Preparing for this requires more than technology. It demands a new science of long-term psychological support, with systems and trained crew members capable of guiding a society through a unique form of grief and helping them build a new identity, one that is not tied to a world but to a journey. Just as we must engineer a habitat for the human mind, we must also transform the human body itself for the rigors of this new environment. The human body is not designed for the void. As our starships push further from Earth, the very environment of space begins to rewrite our biology, a slow and inexorable evolution shaped by necessity. We already see the preliminary sketches of this transformation in astronauts returning from the International Space Station. Their bodies, adapted to the constant pull of gravity for a lifetime, rebel in its absence. Bones, no longer bearing weight, begin to leach calcium into the bloodstream, weakening the skeleton. Muscles, especially in the legs and back, atrophy from disuse. Bodily fluids freed from gravity's downward pull shift towards the head, creating a persistent stuffy nose and putting long-term pressure on the eyes and brain. These are temporary ailments for a 6-month tour. But what happens when the journey lasts for decades or even centuries? The problems compound, becoming not a temporary condition to be rehabilitated, but a permanent state of being. Radiation adds another, more insidious layer to this biological challenge. Far from the protective magnetic bubble of Earth, a starship is bathed in a continuous shower of galactic cosmic rays. These are not like the radiation from a medical X-ray. They are high-energy atomic nuclei, remnants of ancient supernova, traveling at nearly the speed of light. Each one is a microscopic bullet capable of tearing through cells and shredding DNA. The damage accumulates silently over years, increasing the risks of cancer, cataracts, and neurodegenerative diseases. Shielding can help, but stopping these particles completely would require impractically thick walls of lead or water. So we must look inward to the very code of life for a solution. Could we one day edit human genes to enhance our natural DNA repair mechanisms, or to create cellular structures more resilient to this cosmic barrage? This is not mere speculation. Scientists are already studying extremophiles on Earth, creatures like the tardigrade that can survive lethal doses of radiation, to understand the genetic tricks that could one day protect human travelers. To combat the ravages of microgravity, we may need to recreate the one force we are leaving behind: artificial gravity, generated by a slowly rotating section of the starship, seems like the most elegant solution. A spinning habitat would create a centrifugal force, pressing inhabitants outward against the hull, which would then serve as the floor. This would give bones a reason to stay strong and keep fluids settled in their familiar places. But if such a design proves too complex or energetically costly, the alternative is a constant pharmaceutical and exercise regimen. Future spacefarers might rely on a daily cocktail of drugs that signal their bodies to maintain bone mass and muscle tissue, combined with rigorous workouts in specialized resistance machines. Over a single lifetime, these interventions would be a manageable routine, but over multiple generations, something more profound would occur. An isolated population, living under constant, low-level radiation and perhaps even in fractional gravity, would be subject to the unyielding pressures of natural selection. The individuals best suited to that environment, Those with a genetic predisposition for strong bones in low G or a higher natural resistance to radiation would be more likely to thrive and pass on their genes. Consider the parallels to our own ancient history. Human populations that migrated to high-altitude regions like the Tibetan Plateau over thousands of years developed physiological adaptations like larger lung capacities and more efficient oxygen use in their blood. In a similar way, a population confined to a starship for dozens of generations might subtly change. Their skeletons might become denser to counter the slow leaching of calcium, or their circulatory systems might evolve to better manage fluid distribution without the steady pull of a planet's gravity. Their very stature might change, optimized for the cramped, tubular corridors of a ship rather than the open plains of Earth. These would not be a new species, but certainly a distinct branch of humanity, physically molded by the demands of their interstellar arc. This biological journey is the silent partner to our technological one. While we are building engines to cross the void, we must also prepare the fragile, living cargo within, a cargo that will, in time, adapt and become something new, a testament to life's relentless drive to fit its environment, even if that environment is a machine sailing between the stars. Transforming a barren world into a living one is the ultimate act of cosmic creation. Terraforming would be humanity's grandest project, a symphony of planetary engineering conducted over millennia. Mars stands as the primary canvas for this ambition, a world with the raw ingredients we need. The process would begin by triggering a runaway greenhouse effect, a deliberate act of planetary warming. We might start by releasing stored carbon dioxide from the polar ice caps, using giant orbiting mirrors to focus sunlight and melt the frozen reservoirs. As the temperature climbs, the thin atmosphere would begin to thicken, trapping more heat and potentially releasing even more gases from the soil in a self-reinforcing cycle. Another proposal involves redirecting ammonia-rich asteroids from the outer solar system to crash into the Martian surface. The impacts would not only deliver vast quantities of the gas to thicken the air, but also release immense heat, jump-starting the warming process. Yet even the most optimistic timelines stretch for centuries, a sobering reminder that this is not a task for a single generation, but for a civilization committed to a future it will never see. The ethical dimension of this endeavor is as profound as the engineering. What if the Martian soil, deep beneath the surface, harbors its own simple, resilient life? Do we have the right to overwrite an entire planetary biosphere, even a nascent one, with our own? This is not a question of science, but of our responsibility as a galactic species. The technological hurdles are equally staggering. We struggle to accurately model and manage Earth's own complex climate systems, so how can we hope to control the atmosphere of an entire alien world? The sheer scale of energy and material transport required defies our current capabilities. This reality has given rise to a more near-term concept, paraterraforming. Instead of changing a whole planet, we would create smaller, self-contained habitats. Imagine vast, transparent domes sealing off entire craters, or cities built within the natural lava tubes that snake beneath the Martian surface. These enclosed ecosystems would be far easier to manage, offering pockets of Earth-like conditions while the slow, grand work of global transformation continues outside. The dream of building new Earth speaks to our deepest instincts as explorers and builders, a testament to a species unwilling to accept the universe as it is. But it also forces a humbling acknowledgement of the gulf between our aspirations and our power, reminding us that the greatest transformations often begin not with changing a world, but with understanding our place within it. Our search for life is often a search for ourselves, a hunt for the familiar chemistry that animates our own world. Yet this approach risks blinding us to the truly exotic. The universe is a much more inventive chemist than we are, and the definition of life may be far more flexible than our single example on Earth suggests. Every living thing we know is built from the same fundamental toolkit: DNA for information, proteins for structure, and water as the universal solvent. But what if another world uses a completely different set of blueprints? Imagine a biology where information is stored not in a double helix, but in some other complex molecule we have yet to even conceive. Or a form of life that breathes a different gas, consumes a different energy source, and thrives in a liquid utterly alien to our own. Saturn's large moon Titan offers a stunning preview of such a possibility. It is a world shrouded in a thick, orange haze with rivers and lakes not of water, but of liquid methane flowing across a landscape of water ice as hard as rock. The chemistry occurring there is profoundly complex, a constant dance of organic molecules falling from the sky. Could this environment sustain life? If so, it would be a form of life so fundamentally different that it would challenge our most basic assumptions. Its metabolism would be unimaginably slow, adapted to temperatures hundreds of degrees below freezing. Its cellular structures, if it even has cells as we know them, would need to function in a solvent that is non-polar and far less reactive than water. Our current life detection instruments, like those on Mars rovers, are meticulously designed to find the building blocks of life as we know it. They would likely sail right past a Titanian microbe, completely missing its unique chemical signature because we were not looking for the right clues. This is why expanding our definition of life is not just a philosophical exercise, it is a practical necessity for exploration. By opening our minds to the possibility of truly alien biochemistries, from ammonia-based life in the subsurface oceans of icy worlds to silicon-based organisms in searing heat, we dramatically increase our chances of making one of humanity's most profound discoveries. Finding life built on a different chemical foundation would do more than just add a new branch to the tree of life. It would reveal that the tree itself is far larger and more diverse than we ever dreamed. This realization would ripple through every aspect of our interstellar ambitions, forcing us to reconsider what it means to be a living thing in a cosmos of infinite variety. The greatest danger of the void is the one you cannot see. Galactic cosmic rays are not like the radiation we know on Earth. They are atomic nuclei, the hearts of iron or hydrogen atoms, stripped of their electrons and accelerated to nearly the speed of light by the shockwaves of ancient supernova. Each one is a microscopic cannonball, carrying immense energy and capable of tearing through the delicate strands of DNA within a cell. This is not a sporadic storm you can wait out, but a constant, silent drizzle that permeates everything. A ship's hull alone is not enough. Lead shielding, ironically, can make the problem worse by causing these high-energy particles to splatter, creating a secondary shower of even more radiation inside the ship. The solution lies in lighter, smarter materials. Layers of polyethylene, rich in hydrogen atoms, are far more effective at absorbing this barrage. Some concepts go even further, proposing to generate a powerful magnetic field around the entire vessel, a miniature version of Earth's magnetosphere that would gently deflect these charged particles away like an invisible umbrella. Then there are the impacts you can hear. A micrometeoroid, no larger than a grain of sand, travels at speeds exceeding 100,000 miles per hour. At that velocity, it carries the kinetic energy of a bowling ball dropped from a skyscraper. A direct hit on a critical component could be catastrophic. The classic defense is a Whipple shield, a system of spaced layers. The outer bumper, a thin sheet of metal, is designed to vaporize the incoming particle upon impact. The resulting cloud of gas and debris then spreads out, its energy dissipated harmlessly against the main hull behind it. Future ships might be clad in self-healing materials, polymers infused with liquid resin that automatically seal a puncture, much like a scab forming over a wound. But the environment holds more subtle threats. Vast, dark molecular clouds drift between the stars, regions of cold gas and dust so dense they can blot out the light from stars behind them. Plunging into one could not only obscure celestial navigation, but also slowly abrade the ship's exterior with countless microscopic collisions. Even gravity itself becomes a hazard to be mapped. A stray course that passes too close to a rogue planet, a dark world wandering the galaxy untethered to any star, could pull a ship violently off its trajectory. The error might be small at first, a deviation of a fraction of a degree, but over light years that mistake multiplies, sending the vessel hopelessly off course into the endless dark. And the journey's end holds its own perils. The destination star, a seemingly welcoming sun, could suddenly erupt in a violent solar flare, bathing the approaching ship in a wave of X-rays and charged particles just as it is most vulnerable. This would demand immediate, autonomous course corrections, a last-minute dance to find a safe orbital approach. Surviving these myriad dangers requires more than just strong walls. It demands a ship with a kind of robotic immune system. Redundant systems for every critical function, from life support to propulsion, would allow the vessel to isolate damage and reconfigure itself. Swarms of internal repair bots would be ready to scuttle through access tunnels, welding broken lines and replacing fried circuitry. The ship must be built not just to endure, but to heal. Every one of these challenges forces us to confront a humbling truth. Space is not a passive backdrop for our journey, but an active, dynamic, and often hostile environment. Our success will be measured not by the speed of our engines, but by the resilience of our craft and the foresight of our planning. This profound silence leads us directly to one of astronomy's most haunting questions. If the universe is so vast and ancient, teeming with potentially habitable worlds, then where are all the other spacefarers? The physicist Enrico Fermi famously captured this puzzle in a single, blunt query: where is everybody? This is the Fermi paradox, the stark contradiction between the high probability of extraterrestrial civilizations and the utter lack of any observable evidence for them. We have never intercepted a single alien broadcast, never found a relic of another intelligence, never seen the telltale signs of galactic engineering. The cosmos appears silent, and that silence is deafening. Proposed solutions to this mystery force us to confront some of the most profound possibilities about life and intelligence itself. One deeply sobering idea is that technological civilizations inevitably contain the seeds of their own destruction. Perhaps every society that reaches our level of advancement soon discovers a technology, whether nuclear, biological, or something we have not yet conceived, that leads to its swift collapse. In this scenario, the Great Silence is a cemetery quiet, a warning that the window for interstellar travel might be tragically brief. This connects to the chilling Great Filter hypothesis. It suggests that somewhere along the evolutionary path from non-life to a spacefaring civilization, there is a step so improbable that it acts as a near-total barrier. This filter could lie in our past, meaning the emergence of intelligent life itself is a cosmic fluke, and we are the first or the only to have made it this far. Or, even more ominously, the Great Filter could still lie ahead of us, an obstacle we have not yet faced and may not survive. Other explanations are less dire but equally mind-bending. Maybe advanced civilizations are out there, but they have evolved into forms we simply cannot recognize or communicate with. Their technology or consciousness might be so far beyond our own that their activities are indistinguishable from natural phenomena to our primitive senses. Alternatively, they might be deliberately avoiding contact, following a strict policy of non-interference with developing species like our own. Perhaps we are like an isolated tribe in a vast rainforest, living our lives completely unaware of the global civilization that surrounds us but chooses not to disturb our development. Or the answer could be more practical. The galaxy might be buzzing with activity, but we are listening for the wrong things, using the wrong methods, or searching on the wrong timescales. A civilization only a few thousand years more advanced than us might use communication technologies as far beyond our radio telescopes as the internet is beyond smoke signals. How do we even begin to look for something when we do not know what we are looking for? The resolution of this paradox will fundamentally shape our interstellar ambitions. If we are alone, then we are the pioneers, tasked with the solemn and lonely responsibility of spreading life through a barren galaxy. But if the silence is an illusion and the galaxy is already full, then our journey becomes one of finding our place in a cosmic community, with all the wonder and peril that entails. Our current position is uniquely privileged, and the choices we make now will determine which answer to Fermi's question we ultimately discover. The search for cosmic company may require us to look for more than just a whisper on the radio. What if the proof we seek is not a signal, but a silent, abandoned city, or a derelict probe drifting in the cold of our own outer solar system? This is the frontier of interstellar archaeology, a field that shifts the search from the electromagnetic spectrum to the physical realm, hunting for the material leavings of a civilization that may have risen and fallen before Earth even cooled. Instead of listening for a hello, we would be sifting through the cosmic sands for artifacts. These could range from the small and subtle, like a dormant, ancient probe hiding among the asteroids, to the staggeringly vast, like megastructures built around entire stars. The most famous of these theoretical constructs is the Dyson sphere, a hypothetical swarm of energy-collecting satellites that would encase a star to harness its total power output. From our vantage point, such a star would not shine brightly in visible light, but would glow with an intense infrared signature, the waste heat from an unimaginable civilization. We have already observed stars that behave strangely, like Boyajian star, which dims in bizarre, irregular patterns that natural explanations struggle to fully account for. While the most likely answer is always a complex natural phenomenon, such as a swarm of comets or interstellar dust, the very existence of these anomalies forces a valuable question. How would we recognize technology that is 1,000,000 years more advanced than our own? Its appearance might be indistinguishable from nature to our uneducated eyes. A seemingly ordinary moon could be a hollowed-out world, or a wandering asteroid might be a parked vessel. Finding such an artifact would be more than just confirmation that we are not alone. It would be a cosmic treasure trove, a time capsule filled with potentially revolutionary knowledge. We could learn principles of physics and engineering that would take us millennia to discover on our own, accelerating our own journey to the stars by leaps and bounds. This search demands a new kind of observation, one that scans the heavens not just for the chemistry of life, but for the geometry of intelligence, for patterns and structures that simply should not exist according to our current understanding of the cosmos. It requires a profound open-mindedness, a willingness to consider that the most extraordinary objects in the universe might not be natural at all. Whether we ultimately find a silent galaxy or a single alien wrench floating in the void, the very act of looking transforms our perspective, teaching us to see the universe not just as a collection of natural wonders, but as a potential library of ancient cosmic achievements. A single human lifetime is a flicker against the timeline of an interstellar voyage. To reach the stars, we must learn to think in timescales that dwarf our own existence, planning for a future whose architects are dust and whose inheritors speak languages not yet born. This is the challenge of the long now, a perspective that stretches our vision across centuries and millennia. Our entire civilization is built on short cycles, from quarterly earnings reports to 4-year political terms. These rhythms are ill-suited for projects where the first course correction might not happen for 50 years, and the first data packet could take a century to arrive. We must cultivate what the Long Now Foundation calls the deep time horizon, a mindset that treats the distant future with the same weight and consideration as the present. History offers us glimpses of this capability. The great cathedrals of Europe often took more than 500 years to complete. Generations of stonemasons dedicated their lives to a vision they knew they would never see finished, trusting their children and their children's children to carry the work forward. The pyramids stand as silent monuments to this multi-generational commitment. These projects succeeded because they were anchored in stable, enduring cultural and belief systems that provided a continuous thread of purpose. Our modern world, with its rapid technological and social upheavals, lacks that kind of stability. A mission launched today could be defunded by a parliament in 10 years, or its purpose questioned by a society 5 generations from now that has entirely different priorities. This forces a radical idea that interstellar travel may require us to invent new social structures entirely. We might need dedicated organizations, charters, or even trusts that are legally and financially insulated from the short-term turbulence of politics and markets. These entities would be the guardians of the long now, stewards of a mission whose completion is their only shareholder value. Adopting this cosmic perspective is more than an engineering requirement. It is a profound maturation of our species. It marks a transition from a civilization obsessed with immediate gratification to one that acts as an architect for a future it will never personally inhabit. It means planting trees under whose shade we will never sit, but whose branches will one day touch the stars. This shift in how we value time itself may be the most important transformation on our journey, for it prepares us not just to travel through space, but to secure humanity's ultimate fate among the galaxies. The ultimate vessel for an interstellar journey may not be a ship at all, but a stream of pure information. As we project our vision across the vastness of cosmic time, a startling possibility emerges. The intelligence that finally charts the galaxy might not be the soft, fleshy, water-dependent beings we are today. Our current form, perfected for the savannas of Earth, is incredibly fragile for the unforgiving realities of deep space. Yet our own technological trajectory points toward a profound evolution. The rapid convergence of artificial intelligence, genetic engineering, and direct brain-computer interfaces suggests that human consciousness itself is on the verge of a great migration. We could one day choose to leave our biological bodies behind, uploading the intricate patterns of our minds into more durable, upgradable substrates. An uploaded consciousness would not need air, water, or food. It would not suffer from bone density loss or radiation sickness. It could travel at the speed of light as data, a coherent stream of self-aware information beamed toward a distant star system. Upon arrival, advanced robotic factories, perhaps built by earlier, slower robotic probes, could use the raw materials of asteroids or moons to construct physical bodies for these mines, or host them within planetary computational networks. The journey of 1,000 years would feel like an instant, a file transfer between stars. This is not the end of humanity, but a potential new chapter for it. Alternatively, we may choose a different path of transformation, not abandoning our biology but radically reshaping it. Through advanced genetic engineering, we could design human variants specifically adapted to their new homes. Settlers bound for a high-gravity world might engineer themselves with denser bones and powerful muscles. Those destined for a planet with a thin atmosphere could be redesigned to metabolize different gases or withstand higher levels of cosmic radiation. We might even incorporate synthetic components, creating resilient cyborgs perfectly suited for the industrial work of building a new civilization. These specialized post-humans would diverge from one another, each lineage optimized for its own unique world, becoming as distinct from the original human form as we are from our earliest ancestors. This inevitable transformation forces us to confront the deepest questions of identity. If your mind is running on a synthetic processor, are you still you? If your body is more machine than flesh, where does the human being reside? The continuity of self may not be found in the specific atoms that compose us, but in the unbroken pattern of our memories, our thoughts, and our consciousness. This transition from biological to post-biological intelligence might be a natural, perhaps even necessary, step in the evolution of a spacefaring species. Biological bodies are a magnificent starting point, but they represent a fragile and temporary vessel. Our true cosmic destiny may be to shed that initial form, allowing our minds to become the permanent citizens of the galaxy, free from the limitations of the world that gave us birth. Preparing for the stars, therefore, is not just about building better rockets. It is about preparing for our own evolution, a metamorphosis that will complete our journey from earthbound creatures to true citizens of the cosmos. Our journey across the cosmic ocean has reached its final horizon for now. From the first sparks of nuclear thermal rockets to the deep time thinking required for generation ships, we have traced the incredible arc of humanity's potential path to the stars. We have seen how the challenges are not merely technical puzzles, but profound tests of our biology, our psychology, and our very ethics. The vessel that carries us must be more than metal and fire. It must be a resilient world, a just society, and a symbol of hope cast into the void. The potential reward is a future no longer measured in fleeting centuries, but in the expansive billions of years of our galaxy's life. Carl Sagan's words echo here, reminding us that exploration is not just something we do, it is who we are. We are the descendants of wanderers who crossed continents and oceans, and the stars are our next natural frontier. This journey is the ultimate expression of our restless spirit, a refusal to be bound by the atmosphere that cradled us. The future of humanity is a story that remains unwritten, its pages blank and waiting. The choices we make today in our labs, our legislatures, and our collective imagination will author the next chapter. Will we choose to remain, a beautiful but solitary bloom on our pale blue dot? Or will we muster the courage to plant the seeds of our civilization in the soil of other worlds, ensuring that the light of consciousness endures long after our sun has faded? The greatest adventure in all of human history is calling. It begins not with a countdown, but with a decision. We would love to hear your thoughts on humanity's interstellar future in the comments below. And if you want to continue this journey with us, please subscribe.